So in this video, I want to talk about states of matter and then changes in state. So there's actually 5 states of matter. And honestly, if you were to Google states of matter, which I did right before I started making this video, there's actually one link that says there's 7 with some strange things that I've never heard of that are probably maybe talked about in a physics course. But in chemistry, we're going to talk essentially about 3 states of matter. So solids, liquids, and gases. There are plasmas, and then some others ones out there, but solids, liquids, and gases, so those are the ones we're going to be concerned about. So states of matter. Sometimes called phases, not matters, states of matter, or phases. I use states more commonly than I do phases. When I start talking about changes, though, I'll often say phase changes. If there's more than one word for the same thing, I often will switch them without really thinking about which one I'm doing because they're just synonymous in my head. So I don't often differentiate between them. So I'm sorry if that can be confusing, but states of matter and phases are going to be the same thing. Those are going to mean exactly the same. So the ones I want to talk about, solids, and we'll leave some space here because I'm going to write underneath them, liquids, and then gases. And kind of the easiest way to differentiate between these is to think about the particles that make them up and then how they're connected. So in a solid, these are my particles that are making up my solid, and they're really well connected to each other. So this particle is connected to that particle, these are connected to each other. There's different types of connections depending on what type of solid it is, but these guys are all connected to each other. They're pretty close to each other because they're connected. Because there's lots of connections, it really functions as a unit. So lots of connections. Between the particles. Because of that, they're close together. And then because of all those connections, like I had said, it really functions as a thing. So if I was to take a solid and tip it on its side, then the entire solid tips on its side, right? Its shape hasn't changed. It's just now oriented differently. So we would say that it has a definite shape, meaning that the shape doesn't change. It's always going to have that same shape. If I was to take, I don't know, the Apple Pencil that I'm holding and set it on the desk in front of me, it's going to have the same shape as it does when it's in my hand. If I was to go stick it into my coffee cup, it's going to have the exact same shape that it does when it's in my hand, right? All of those particles are connected to each other, so its shape doesn't change. It has a definite shape. It also has a definite volume. And if you guys remember from your chemistry past, volume is the amount of space that something occupies. So it's always going to occupy the same amount of space. Again, if I was to take my Apple Pencil and go set it on the desk, it's not going to expand and occupy a different volume, right? A different amount of space than it does when it's in my hand. So a definite shape and a definite volume. The reason for that is that those particles are really, really well connected. When we go from a solid to a liquid, what we're doing is we're breaking some of those connections. So if I was to go and look at my solid over here, right? Sorry guys, I'm grabbing my pencil. If I was to look at this solid, what we're doing when we go to a liquid is we're breaking connections. We'll see if I can break a connection without erasing the whole thing. Nope, can't do it. Let's just redraw it. So let me put that back. So I have these guys, and they were connected, so let's pretend those pink things are still there. And let's say this is still connected, and that's still connected, and that's still connected. But I broke those connections across the top. So what can happen now is this particle can swing over here. It's still connected, right? It's still connected, but my shape is now slightly different. This particle here, it's going to swing out over here. So it has a slightly different shape, right? We have some connections, but not lots of connections. They're not super close anymore. They're kind of floppy. So some connections between particles. Right? So because of that, my shape can change, right? When those couple particles moved out, it now has a different shape. So we would say it has an indefinite shape. The shape of that depends on the shape of the container or whatever it happens to be in. So I have a cup of coffee on my desk. If I was to take that coffee, which is currently coffee cup shaped, and dump it out onto the desk, it's going to spread out and have a different shape than when it's in my cup. So an indefinite shape. The volume, however, the amount of space that it takes up, is going to stay the same. My coffee isn't going to expand and take up more space. It's just that the shape of the space that it takes up is different on my desk, but it still takes up the same amount of space. So a definite volume. Right? Those particles, if I go back and look at these guys, these particles are still connected. Right? They were able to move, so the shape is different, but for the volume to be different, I would have to actually completely disconnect them and have them spread out or contract, which is actually what happens when we have a gas. So in a gas, I have no connections between particles. We actually have a chapter entirely on gases, and then liquids and solids share a chapter because gases have no connections. They're so different. Liquids and solids still have connections. Solids more than gases, but solids more than liquids, but they still have connections. Gases, no connections between particles. So this particle, if it wants, it can go out over here. And this particle here, it can move over here. And this particle, I lost two of them. Those particles, let's say they want to squidge closer together. So the shape changes because I have no connections, but the volume can also change, right? Because they're not connected at all, it can expand, or we can also compress it. So it has an indefinite shape. So if I had gas in my coffee cup and I had a lid on it, it would have the shape of my coffee cup. It would also have the volume of my coffee cup. Right? The amount of space that it would take up, it would expand and fill that entire cup. If I was to then take the lid off of it, then the gas is going to escape, and eventually it's going to fill up the entire room that I'm in. So its volume is now going to be room-sized, right? That's going to be the amount of space it takes up, and then the shape is going to be room-shaped because it's going to expand throughout the entire room. So, again, kind of the differences between these guys. Not one eraser, sorry. Lots of connections, some connections, no connections, right? Because I have lots of connections, the shape and the volume, both of them do not change depending on their situation, right? Depending on the container that they're in. Liquids, because I have some connections, its shape can change, but I still have connections, so the amount of space it takes up my volume is not going to change. Gases, no connections at all, so shape can change and the volume can change. So state changes in state next, or phase changes. So when we go from a liquid to a solid, or solid to a liquid, or gas to a solid, phase changes. So let's talk about temperature real quick. I know this is kind of displaced, but temperature, we can define it as the average kinetic energy of a substance. Kinetic energy is energy in motion. So essentially we can say is that as we heat our substance up, our particles move faster. So something with a higher temperature has particles that are moving with more energy. Something that is at a lower temperature has particles that are moving with less energy. So if I was to heat something up, what I'm essentially doing is I'm making the particles move faster. If I cool something down, those particles are moving slower. So higher temperatures, particles move, and I'm going to use the word faster. They're really moving with more energy, but it's easier to think about if we think about it as faster. Lower temperature, particles move with less kinetic energy. We're going to say slower because it's easier to think about it that way. So when I undergo a phase change, if I take a solid, right, if I go back up here to my solid with lots of connections between particles, so even as a solid, those particles are moving. They're connected to each other, so they're not moving a lot, right? I have lots of connections. They're close to each other, but they're still jiggling. Unless we're at absolute zero, and we'll talk more about that when we review temperature officially later, unless we're at absolute zero, they're moving. Even in a solid, if I put the hands on my desk that are in front of me, I can't feel the particles that make up this solid desk moving, but they are. There's little vibrations that are going on. As I heat that solid up, I'm causing those particles to move faster. Now remember, they have connections between each other, right? These guys are all connected. And I usually use an example, and if we were in class, sometimes I make you guys do this. If we were to stand up and all hold hands, right? We're a solid because we have lots of connections. And then we start jumping around a little bit, start moving. Some of us are going to end up losing that connection, right? If the individual particles start moving faster, sometimes you're going to end up losing that person's hand. It's going to be hard to hold on. If that person's jumping up and you're jumping away, you're going to break that connection. So that's what's happening when we're going to a liquid. The particles start moving faster, we start breaking those connections, now we have a liquid. We continue to heat it up, those particles move faster, right? They have more energy. So now those of you that are still holding hands, you have to start like whipping in circles and going crazy. And eventually all of you guys are going to lose connections. No one's going to be holding hands anymore, and we're a gas, right? No connections between particles. So as we increase the average kinetic energy, right? As we increase that energy in motion, it's harder to maintain those connections. And we go through the solid, liquid, and gas states. We start slowing it down, you can reform those connections. So again, it has really to do with those connections between particles. I do want you to know the names of some of those changes. So if we go from a solid to a liquid, I think most of these, you guys know what is that called. If I stick an ice cube on my desk and it melts, oh, I just gave it away and it turns to a liquid. What just happened? It melts. So melting. If I go from a liquid to a gas, it is evaporated. We could say it's vaporized. The process is boiling. We could say that too. You can go from a solid all the way to a gas. And not all substances can do this, but some can, without actually going through the liquid phase, and that's going to be called sublimation. Dry ice, which is solid carbon dioxide, is one of those. If you were to take a solid chunk of dry ice, it's going to go right to a gas. You're not going to have liquid carbon dioxide. It's something that sublimates. So sublimation. All of these are requiring energy, right? To go from a solid to a liquid, we put energy into breaking those connections. From a liquid to a gas, we put energy into breaking those connections. Solid to a liquid, same thing. So these all require energy. And then if I was to turn all of those arrows backwards, right? If I went from a gas to a liquid, condensation. If I was to go from a liquid to a solid, what are we doing? Yeah, freezing it. And then this one is less common again. It's probably the one that more people forget. From a gas all the way to a solid. Any takers on this one? Do you guys know it? Yeah, this one's deposition. I wouldn't beat yourself up if you don't remember it. Most people don't. We just don't see it a lot. Frost is a good example of that one. I don't know that you ever get frost in Arizona. How many of you guys have ever seen frost? That's a good question. But these guys are going to release energy. So do you be familiar with those terms? Kind of an example I could give you, I could say, I got water, and then I'm going to put an L after it. We can review that too here in a second. And then I'm going to put water with an S after it. And then I can ask you what type of change occurred. I went from a liquid to a solid. Going from a liquid to a solid is freezing, so that would be my answer. So things that are, I said I would review it. If I have something that's solid, so if I wanted an ice cube, you put a little S after it for solid. If I wanted liquid water versus solid water, and then if I wanted water vapor, I put a G. So S for solid, L for liquid. You guys could probably figure this one out all on your own because you're smart. G for gas. So next I want to talk about chemical versus physical properties and changes, both. So physical first. Actually, we'll do them again together. So versus chemical. And I'm going to do changes and then I'll mention properties, but if you can understand the difference between the changes, then properties are basically the same definition. You're just not changing. You're just looking at a property. So kind of the big difference between these is that a physical change, you're not changing what the substance is. So if you start out with water, you end up with water. If you start out with cellulose, you end up with cellulose. So it's a change that doesn't involve changing the chemical identity of the substance. Chemical changes do involve changing the chemical identity. So if you start with water, you're going to end up with something that's not water. If you start with cellulose, you end up with something that's not cellulose. So a physical change involves no change in the chemical identity, or you could just say identity, of the substance. A chemical change does involve a change in the chemical identity of the substance. So with a chemical change, you're making something entirely new. With a physical change, you're not making anything new. You're making the same thing, it's just changed in some way. If we wanted to change a property, a physical property is one that you can determine without changing its chemical identity. A chemical property is one that you determine by changing the chemical identity. So it's essentially the same definition. Right here, a new substance is produced. With a physical change, it can look drastically different, but it's still the same identity. A common example of a physical change are changes in state. Please, if I ask you to define a physical change, don't say changes of state. A change in state or a phase change is an example of a physical property, but that's not what it is. And they're not the only type. Like if I was to cut my hair, right, it's still solid. I have solid hair now. It's not a gas or a liquid. And if I was to cut it, it would be shorter, but it would still be solid. Right? If I was to take a sheet of paper, so cellulose, and tear it up into a whole bunch of little pieces, it's still cellulose. It's still solid, right? It's not a change in state, but it is a physical change. So we can put under their examples, if I went from any sort of solid, water solid, to water liquid, right? That would be an example if I wanted to tear a piece of paper into tiny pieces, or just even crumple it up. That would be another example. So changes in state, are physical changes, but they're not the only type. So a lot of times coming out of lower level chemistry classes, that's how students will define it when I ask. If we were in class, I would ask you guys, so what's a physical change? And every year for the last 20 years, folks reply with changes in state. That's not what it is. That's an example. So be careful not to define something with an example. If I ask for a definition, it's a change that doesn't involve a change in the chemical identity. Right? With this one, I started out with H2O, I end up with H2O. They're physically different. One is solid, one is liquid, right? One I have lots of connections between particles, so it has a definite shape. The other I have some connections between particles, so I have an indefinite shape, but it's still water. And then again, just be careful. Whoa, not a highlighter. Not just changes in state or phase changes, right? There are other examples, so just be careful on that. Chemical change, we can use water again if I wanted. We'll use liquid. And if I was to undergo electrolysis, I could break it into hydrogen and oxygen. And this isn't balanced. We'll talk about balancing coming up here. But I would need 2 waters for every 2 hydrogen and 2 oxygen. But the part that's important is that here I have, I'm going to get my pen choices right here at some point. I have H2O. Here I have hydrogen, right, an element, separate from oxygen. Another common example, we could do rust. If I take iron, solid, and then I take oxygen gas from the air, I end up with rust, and rust is iron 3 oxide. And again, this one isn't balanced. I'm not going to bother to balance it now, but the point is that what's here is not what's here. They're different things. If I was looking at a physical change, I would have the same chemical formula on both sides of that arrow. So physical, no change in the chemical identity of the substance. I'm not making anything new. It just looks different. Chemical change does involve a change in the chemical identity. Combustion would be another example. You would take some sort of carbon, hydrogen, it could have other elements in it, but often carbon and hydrogen, you would add oxygen to it, you get carbon dioxide and water as a product. So combustion would be another. There's a lot of examples of chemical changes. Chemical changes are just chemical reactions. Real quickly, I do want to touch on the difference between an extensive versus an intensive property. I don't use these a whole lot, but they are one of the objectives from this chapter, so I just do want you to know the definitions between them. But an extensive property is a property that depends on the amount of your sample. An intensive property is one that does not depend on the amount of your sample. This depends on sample size. Hopefully this will make more sense when I give you some examples here in a moment. Does not depend on sample size. So some examples, extensive, we could say the mass of something, right? Mass is defined, and I haven't written this down yet. I will in part 2 of this chapter, but mass is the amount of matter in an object. So if you have a larger sample, you're going to have more matter, so it's going to have more mass. If I have a smaller sample, it's going to have less matter, so it's going to have less mass. So the mass of something does depend on the sample size. We could say volume, right? If you have a little bit of something, it tends to take up less space than if you have more of the same thing. An intensive property, we could do density. And we will review density in more detail in part 2 of chapter 1 also, but density is mass per volume. So if you have a larger sample, your mass is going to be bigger, but your volume's also going to be bigger. So when you divide them, you're going to get the same answer as if you have a smaller sample size, because then both the mass and the volume are smaller. Let's say, just for kicks, if I had 12 for my mass, I'm not even going to put units on it, but let's just say it's 12, I would lose a ton of points for no units there. And then I want to divide that by 4. That's going to be my volume. So I'm going to get a density of 3. If I had a smaller mass, 6, it's also going to take up less space, so 2, and then my density is still 3, right? So this came out to be the same, because if I have a bigger sample, both the mass and the volume are bigger. If I have a smaller sample, both the mass and the volume are smaller. When I divide them out, it comes out to be the same. So it doesn't depend on how much I have. The last thing I want to talk about in this video is the law of mass conservation, and it's kind of displaced as far as the flow of this lecture, but it is important, and we're going to come back to this quite a bit this semester. So since we've been talking about mass, I just want to throw it in here. And the name of the law really tells you what it is. It tells us that mass is conserved, and it's during a chemical change. So if you have, we go back up to these examples here, and this is why I needed to balance it. It's the whole reason we balance reactions. If I start out with water and then I end up with hydrogen and oxygen as products, the mass of that water that I started out with is going to be equal to the sum of the masses for hydrogen and oxygen. So basically the total mass on this side must equal the total mass on this side, in theory, right? In practicality, sometimes you'll spill some or you don't get every little drop from one beaker to the other, but theoretically, the mass of your starting material is going to be equal to the mass of your finishing material. So reactants and products, if you know those terms. The same here. So that's why this one isn't balanced. I would have to balance it. But the mass here would be equal to the mass here, right? Mass is conserved. So we're not creating mass or destroying mass. We're conserving mass. So mass is neither created nor destroyed. In a chemical reaction. It's not true for nuclear reactions. A little bit different there, but in a chemical reaction, mass is neither created nor destroyed. So the mass of our starting material which are our reactants, is equal to the mass of the ending material, which are our products. So mass is conserved in a chemical reaction, right? We're not creating it, we're not destroying it. Mass that we start out with is going to be the mass that we end up with. Remember mass, I said this briefly a few minutes ago. Mass is the amount of matter. In an object. So essentially, we're conserving matter, right? If I start out with a certain amount of matter, I'm going to end up with the same amount of matter. And that's why we needed to balance it, right? If I had 2 hydrogen over here, H2, then I have to have 2 hydrogen over here, H2. Here I have 2 oxygen, but before I put this 2 in front of it, I only had 1 oxygen, which means I created an oxygen atom, and we can't do that. So if I put a 2 in front of it, sorry, this is so messy right now, I have 4 hydrogen and 2 oxygen. By putting a 2 on the other side, I have 4 hydrogen and then 2 oxygen. So I'm conserving mass, I'm conserving matter. So we're always going to follow this in chemistry. If we start out with a certain amount of matter, we need to end up with that same amount of matter. So the amount of mass is being conserved.